Hello, welcome back. Let's start with the next lesson, which is K-means clustering. So for this lesson, we're going to talk about what is the clustering, what does it mean, what does clustering mean, what K-means clustering means overall, some of the special details, the importance of using the initial centroids, the strengths and weaknesses, procedures, K-means issues, and many other things. Okay, so clustering is the classification of objects into different groups or more precisely the partition of a data set in subsets clusters so that the data in each subset ideally shares some common trait, often according to some defined distance measure. So what a clustering means is imagining that you're in the library and you want to that every group in the library are going to different groups of people who like to hang out with who are athletes or who are the part of the chess club or the rocket team, or the cross country team. So they're gonna all gonna cluster with each other. So they're gonna partition the student population into smaller clusters depending on what their interests are. Now, in this case, when we do a cluster, when we partition these groups, right, this data, what we're doing is we're classifying the group, right? We're saying, okay, because you are in the cross country team, right? You're hanging out with the cross country team. You're in the same group, right? Then you're gonna be a cross country runner, right? Or because you are in the chess club and you're hanging out with the chess people who plays chess, then you are gonna be a chess player, right? So things like that, right? So your cluster, you partition the population of the students into smaller groups. Now, in our case, right, one of the specific ways of defining this clustering is by a distance measure. So we'll talk about that. Partitioning clustering approach. Each cluster is associated with a centroid, a center point. Each point is assigned to the cluster with the closest centroid. Number of clusters K must be specified. The basic algorithm is very simple. The commonest form of unsupervised learning from the raw data as opposed to supervised data where the classification of examples is given. So what we're doing here is we're defining a center. Let's say that we have the library, right? And we decide how many points of references we're going to have in the library. And so imagine that we put there's 4 corners on the library, and we put 4 corners around it, one in each corner. And what we do in this K clustering is, so let me do some drawing there. So imagine that you have your library and you have the student population. So you put some points, random points, you can put in randomly, right? And what you're doing, right, those guys are going to be your centroids. And what you're going to be doing is you're going to create a circle around it, right? So all the people who are near the same distance from that centroid will be part of the same group. So everybody who is near this point will be part of this group. Anybody who's near by a distance will be part of that group. So those are the centroids, right? So we're gonna have a center point and we're gonna have a distance measure from that centroid, and whoever is within the range will be part of that group. So that's how we cluster. So very similar to the way the K nearest neighbor. But in the K nearest neighbor, we're looking for the K closest neighbors. And here we're not. We're actually, the way we're measuring it, how we determine it is by a center point and seeing who is closest to that center point, right? And so in this case, back then, the K represented how many neighbors you were looking around that person to be able to classify. In this case, the K means how many clusters we're gonna have. Here we have K equal to 4. There's 4 clusters. Okay, and we're gonna go a little more detail when we talk about here. Now, this is an unsupervised learning. We don't have to tell the computer who is we don't have to train it in a sense that to tell them the label of each group when we actually put in the data, because all he's doing is actually calculating the distance between the centroid and whoever falls in that range within that scope, then is going to be considered the same class. Okay. K-means clustering details. Initial centroids are often chosen randomly, so we choose those centroids randomly. In this case, in my case, I chose 4. Clusters produced vary from one run to another one. So depending on where you put your centroids, is going to give you a different answer. The centroids is typically the mean of the points in the cluster. So it is the so that will be practically the average distance on the cluster, the centroid. The closeness is measured by the Euclidean distance, cosine similarity correlation. So it's using the Euclidean distance, the distance of 2 points. K-means will coverage by common similarities measures mentioned above. Most of the convergence happens in the first few iterations. Often the stopping conditions is changed until relative few points change clusters. So we had to repeat this process so we can get the most elements that we need. So for example, here, let's say that we have 3 clusters. You can see the three clusters here. Sorry, let me get my. So here you see one cluster, one centroid and one centroid. And each of those centroids is going to form a cluster. So in this point, right now, this is not making a very, correct representation. So if we repeat the process, you can see that the centroids are kind of moving away, right? As you iterate more, again, they're moving away, they're centralizing themselves to get the best efficient format. So you can see now they're retreating back and now falling into the center of the data, of the different data. And now this forms a much better clustering for this data. So, but you can see that the more you iterate, right, the more is going to be changing the shifts of those centroids to form a much better cluster. Now here's another case where we choose the centroids in a different location. So here, if we choose the centroids to start one right here, the other one right here, and the other one right here, so you can see that this is clustering those datas, right? And then you, as you iterate again, that shift, right, is not happening as much. This guy's not shifting as much as it should have been. This one's practically stay the same. It shifted a little more to the center, but this one move a little more to the right. And then you can see again, the green one doesn't move much, the blue one doesn't move much, and then the red one kind of stays in the middle, in the bottom part. So you see doesn't change much in the iterations. So this was not a very good clustering. So it all depends on where you choose your centroids that is going to give you the outcome. So we always want to try different setups, right? Different centroids locations as a start, so that we can actually efficiently improve or find the best efficient location for our centroids. Strengths and weaknesses. Strength, simple iterative method, so it can just process that iteration very freely, very simple, doesn't take that much work. User provides the k, so we're the one who provide that k value, which is called a hyperparameter. The weakness is often too simple, bad results. As you can see, we chose a centroid that it was not the right spot and it didn't give us the best efficient clustering. Difficult to guess the correct k, so it does take a little bit of a while to figure out what the best k will be. Here's an example of a k cluster where we choose where we select 2 k clusters, the blue one and the red one, to select the cells in the seeds on the in the data. So randomly select the initial cluster. So we're choosing 650 and 200 for seed number 2. And cluster C1 will be 650, and then cluster 2 will be C will be 200. The initial clusters represent the mean value of this cluster. And then step number 2, calculate the distance from each object to each cluster. So we're gonna figure out who is the closest, where they belong to. So we're gonna do the type of distance should be used. So we're gonna use the Euclidean, assign each object to the closer cluster. So we're practically gonna assign the different clusters depending on where the distance from the centroid to the. So here's our centroid. Right, here's our centroid, and we did a distance measurement on all the points that we have here, right? And that's how we decided where to draw the line for our K cluster. So everything on the top will be part one cluster, and the other one will be the other cluster. There will be a different classification. But they measure every single object data and see where would they fall. So now we have a different centroid, as you can see. We went from 650 to 708. We went from 200 to 214. And the K-mean cluster, we can iterate. We can calculate the distance from objects to cluster centroids, assign objects to the closest cluster, recalculate the new centroid. So this is practically what happens in the iteration. We're going to be measuring the distance between each data to the centroid. We're going to assign an object to the closer cluster. So we're going to find out which one gives them the smaller distance measurement, and then recalculate the new centroid. So we're going to always shape the clusters so we can find the smallest data differences. We're going to stay on the convergence criteria, no change in the clusters, max iteration. So eventually the change would stop, and that's when we means that it converges, that the changes has stopped, that has settled. Divergent means that that's still fluctuated. K-means issues. The distance measure is a square Euclidean. Scale should be similar in all dimensions. Rescale data, not good for nominal data and Y. So this could actually have a very intriguing problem, because the more data we have, the more distance we have to measure. So that could be a problem there, but we're still using the Euclidean distance measurement, which is not a very complicated formula, but it's still a lot of data will imply that it's going to create a lot more measurements. Approach tries to minimize the width in cluster sum of the squares error. So the within cluster sum of the squares is the WCSS. Implicit assumption that the SSE is similar to each group. And we'll talk about that. So here's the overall within square error within the cluster sum sum square error. So the overall within the cluster sum square error is given by this formula, which is the sum of the differences on the mean. So here we have the differences of the difference between the mean of the cluster, right? This is the cluster's mean, the centroid mean, and then this is the data, that the object's data, the data, and this is going to figure out the differences between them, and we're gonna add them for every K value. And so for every element that we have on the data, and that's gonna give us the within cluster sum error. Now again, we're not gonna have to do that because it's not a math class or an advanced course in machine learning, right? A graduate course. So in the graduate course, you will probably see this in more detail. But for us, we just need to understand that this is just gonna it's gonna measure the error. The goal is to find the smallest within cluster sum error. And does this depend on the initial seed value? And so yes, it does depend, right? Remember, we saw that in our example, if we if we choose a cluster, initial cluster, initial centroid, right? Then it's gonna give us a much better partition. And on contrary, right, if we don't have, we're not lucky enough, we choose the right one, right? Sometimes it's just luck. Then you're gonna have not a very efficient representation of clusterings. So that's why sometimes you want to try this method a couple of times. Okay, so summary: K-means it's easy to use. Need to work to know the K. May need to scale the data. Good initial method. Local optima. No guarantee of the optimal solution. Repeated with different starting values. So this is what it means that we're not guaranteed that we're gonna have that we're gonna get the right answer. So we need to be able to try the method a couple of times. Okay, so that should be the end of this session. We'll go and jump into the next one.